Hello everyone, welcome to the Math 45 Exam 5 review. And so there are 8 questions here we'll be discussing. The exam will have 8 questions as well. They'll be the same type of questions. They will have to do with finding the equation of a conic section given the description of its graph, or like in this problem, find objects to do with the graph given the equation. Now, a lot of the problems we'll be seeing in the review will look like they're in this form. They're in general form, meaning everything to one side, zeros on the other. It won't necessarily be like that for all problems on the exam, so this is kind of preparing you for maybe worst case scenario kind of thing. But still, we'll have an equation given to you, and from there you need to actually convert it to a standard form to actually interpret some objects. So for example, here we're given that this represents the equation of a circle. Now the standard form for an equation of a circle for this problem, just jumping into the problem, is x minus h squared plus y minus k squared equals r squared. Okay, and here the center is the point h comma k, and the radius is r. So it's what's subtracted from x, what's subtracted from y, together as one point, that's the center. And then what's squared on the other side, that thing being squared is r. So basically you have to square root that number. So to get this in that form, notice first off, we need to basically complete the square for x and for y. So to do that, I'm going to grab these x's and these y's, group them together individually in a way so that we can complete the square by adding some number, some constant term, to each of those. So let's see what that looks like. So I want to write x squared plus 6x plus something that'll hopefully complete that square. Do the same thing for y squared plus 8y, but it's going to be a different number. Maybe. Could be the same, who knows. I want to simultaneously actually get rid of that 9 on this side. It's no good to us on this side, so we'll subtract it to that side. And keep in mind, whatever we're adding on the left, we also want to add on the right so that we have a balanced equation. Okay. Now, if there's no number in front of your square term, then this will always complete as x plus half of the middle term, half of the middle coefficient. Half of positive 6 is positive 3, so this is x plus 3 squared. And you can check it out just by expanding out. You get x squared plus 6x plus 3 squared is 9. So we need a 9 here. Okay, that means I need to add a 9 to the other side. And similarly for this one, if you have 8, and again, this only works when there's no number in front of y squared or x squared, just the square term, that is. There's no number in front of the square term. I keep saying x. In front of the square term, then you can do this by just halving the middle one. But if there is a number in front, you basically have to factor that out. We'll actually see that in some problems later on. But for right now, we're just doing this. Halving 8, we get 4. If you expand this out, you get y squared plus 8y plus this squared is 16. So we need to add a 16 to this side. Perfect. Notice, coincidentally, these 9s actually cancel out on the left, on the right side. Or we're just left with 16. So now this is in standard form. To be a little more specific, we can actually get it exactly in this form by noticing a few things. This is supposed to be x minus a number, but it's x plus a number. That's actually not too bad because all we need to do here is just write it as a double negative. X minus negative 3 is the same as x plus 3 after all. Similarly for y plus 4 is the same as y minus negative 4 squared. And 16 we know is 4 squared. So right away, because of this information, we can interpret right away that this is h, this is k, and that 4 is r, just by looking at this and comparing. So we know the center is the point negative 3 comma negative 4, and the radius is just 4 itself. And we're done with this problem. So we'll see the future problems, the rest of the problems in the review for this exam, will basically have some connection to some standard form depending on what the graph looks like. In this case, it's circle. So for conics, there are circles, ellipses, parabolas, and hyperbolas. They all have some specific form that tells you some specific objects. Usually it's a center, radius for circle, and for parabolas you have a vertex, focus, directrix. And for ellipses, as we'll see, we'll have a center, vertices, foci, and there's a few other things, but we'll see them as we go along. And hyperbolas also. They're actually very similar to ellipses, as it turns out. But again, I'll try to emphasize and elaborate as we go along. So it shouldn't be too bad, but we're done with number 1 here. We found the center and radius for the circle. Now let's move on to problem number 2. All right, so for this problem, it says find the equation of the parabola with vertex 3, -2 and focus 0, -2. I want to point out that it actually originally said 3, -1, but that was a typo. In fact, what you'll notice is that for a lot of these problems involving parabolas, and actually for ellipses and hyperbolas as well, the vertex and focus will always share an x or y value. And we'll kind of see that in this problem a little bit, we'll see why, but then we'll also see why when we do ellipse and hyperbola problems. Basically, there's symmetry and they all lie on the same axis of symmetry, basically. Now, how do we get started with this problem? Well, I think the best thing to do is really to plot these points and then try to figure out what we know of parabolas to get some motivation. So I'm going to create an XY table here. It's not going to be to scale, of course, but try my best. Let's go 5 in each direction, I guess. It should be fine. And it doesn't need to be perfect, just to get an idea. Okay. So the points are 3, -2, which is here and down here. So I'm going to label this point as V for vertex. Let me label that actually in front of this. And then the focus I'll label as F for focus. That's 0, -2, just to be specific there. Okay. So at 0, -2, that is down here. X equals 0, Y equals -2. So that there is the focus F. The X value, the Y value is -2. Okay. Now, what do we know about parabolas? Well, we know parabolas open from the vertex. They stem from the vertex and open in the direction of the focus. Focus is in the interior of the parabola. So this must open like this. It must open to the left. Perfect. Okay, what else do we know? Well, we know the distance from the focus to the vertex is what we call P. There are different interpretations of this, but let me try to remind us of what the standard form looks like for parabolas. So for parabolas, you have horizontal and vertical scenarios. Try to emphasize on each of these. The horizontal, let's talk about vertical first because it's something we're kind of more familiarized with just earlier on in algebra. So very similar with a circle, we have x minus h and y minus k. Now, what's with this square and the 4p? Well, let me try to explain a little bit. So we know vertical parabolas are functions of x. Usually we see y in terms of x and x squared and so on. It's quadratic in x. So that explains why there's a square in x. The 4p we'll talk about in a second. But now, looking at this, one of them is squared and the other one has a 4p in front. The one that's squared is not the variable that you think of as far as orientation goes. For example, vertical reminds you of y's, and the y factor here is not squared. Okay, so similarly for horizontal, y minus k will be squared now, and x minus h is going to be multiplied to 4p. Okay, now what exactly is p? Well, p is the distance from the vertex to the focus. And also from the vertex to the directrix, which we're not going to be talking about in this problem too much. But basically, if you were to travel the same distance in the opposite direction, 3 in this direction, you will land at x equals 6. So this x equals 6 is actually the directrix, which I label as capital D. Okay. Great. So that's kind of all we need to know. The only issue is that there are different versions of these. Sometimes p is negative, or can be negative. Sometimes it can't be. For this scenario, for what I want to lay out, is that p can be negative. So when we're talking about distance, we're really talking about the absolute value of p. And let me emphasize that if p is negative, then that means for horizontal scenarios, so this is true for horizontal or vertical. This statement here is true for horizontal or vertical. But for horizontal, p being negative means it would open in the negative direction, and p being positive means that it would open in the positive direction. And for vertical now, just kind of emphasize what is really going on here. When p is negative, it opens in the negative vertical direction, and when p is positive, it opens in the positive vertical direction. Great. I hope that's clear. And the absolute value of p is the distance. Now notice here the distance from f to v is 3. It's the distance from 0 to 3 there on the x-axis. So that's 3. What does that mean? That means the absolute value of p is 3. So we found that out. So what does that imply? That implies that p is either positive or negative 3. But since we have this scenario opening in the negative direction, this actually implies p is negative 3. And the vertex is h comma k, which I didn't actually say here. So maybe I should have also emphasized that the vertex is h comma k for both of these scenarios as well. So let me kind of put those in one note here in between. And with that being said, notice for each of these, all we really need is h, k, and p. X and y stay x and y. Those are variables. But p, h, and k, those are actual numbers. So once we have those, we're good to go. Also, we need to figure out what scenario this is. We already said this is a negative p scenario for horizontal because it's facing in the negative horizontal direction. Perfect. So I know to use this equation. I know what h and k are from the problem. And based on the distance from the vertex of the focus, we actually found out what p was. So what does that mean? It means we're done. Let's plug it in. So we have y minus k. What's k? Negative 2. So y minus negative 2. Okay, is that squared? Yes, it is, because it's y. Right? It's the one that's not the direction. The direction is horizontal, so that's x. The x one is not squared. So now, we have for p. P we found to be negative 3 times x minus h. What's h? H is 3. Plugging those values in, simplifying a little bit, we get y plus 2 quantity squared is equal to negative 12 times x minus 3. This is really all I'm asking for. Just to simplify a bit, you don't have to go all the way into general form or anything like that. This is fine, and that concludes this problem. We found the equation, perfect, and now we can move on to question 3 now. All right, so for this problem, we're asked to find the equation of the hyperbola with vertices negative 2, 4, and negative 2, negative 6. And foci, negative 2, comma negative 1 minus 3 radical 3, and negative 2, comma negative 1 plus 3 radical 3. Now there's kind of a hint embedded into the foci part, and that's that if you ignore this negative and positive 3 radical 3, you get negative 2, comma negative 1. So that actually will be the center. I'm kind of spoiling some things, but really we should do what we did with the last problem. We should plot these points. So let's plot these points. We're going to need a little bit of space here. Something to notice is that everything has the same x value, negative 2. So this is all on the same vertical line, x equals negative 2. So let's see if we can plot these. So negative 2, comma 4 is up here. Negative 2, comma negative 6 is way down here. So these are the vertices. So I'll call these V1 and V2. Doesn't matter what you call them, as long as they're each V's. I'm just distinguishing between the two of them. So we have opposite facing parabolas, basically. That's what a hyperbola is. Opposite facing parabolas, you have vertices and you have some foci. And you have a center as well. Now the foci I haven't really plotted yet, but what you'll notice is that if you actually find these values, you'll have to approximate them maybe. 3 radical 3 minus 1 is actually going to be a little bit above 4. So it'll be somewhere over here. I'll call that F1. And then negative 1 minus negative 3 radical 3 is actually going to be somewhere below negative 6. So I'll call this guy F2. Not being exact, but that's more or less what it looks like. Now, the visual way of doing this is to look at this vertical line that goes from V1 to V2 between the vertices. And notice the center is going to have to meet halfway in between. So we can just count this distance, 6 and 4, that's a total of 10 units. And if you half that, you get 5, excuse me. So that gives us, leads us right here to negative 1. There we go. So that's also 5 if you count. So indeed, the center is going to be at the point negative 2, comma negative 1, like I predicted earlier. So that's the center. So the center by symmetry we found to be negative 2, comma negative 1, and that's h, comma k. Great. So far, just by using a little bit of knowledge of hyperbolas, we have this. Now we want to find the equation of the hyperbola, and I haven't shown you the standard forms for the equations of the hyperbolas. I'll do that over here, I think. So the standard forms for the equations of the hyperbola are either x minus h squared over a squared minus y minus k squared over b squared equals 1, or y minus k squared over a squared minus x minus h squared over b squared equals 1. So what's the difference here? Well, the big difference is that we have a different leading term, basically. So when x is in front, this is actually for the horizontal scenario. And when y is in front, this is for the vertical scenarios. Probably need to lecture a little more here just so we understand what's going on. Now, for a horizontal hyperbola, you'll have two opposite facing parabolas. With the center, you have vertices and you have foci, which are the focus for each of those parabolas, basically. Okay, so that's what that looks like for horizontal. For vertical, it'll look kind of the same, only tilted. Two vertical opposite facing parabolas with a center halfway in between. The vertex of each of those are the vertices, and then each of those parabolas has a focus. Plural is foci. Okay. Now, what about this A and B? Well, what I'm going to say for one is actually true for the other. I'll just use the top one as an example. So the distance from the center to a vertex is what we call A. The distance from the center to a focus is what we call C. What is B? Well, B is actually the distance from the center to a minor axis endpoint, which basically lives on what we call the dotted box, or what I call the dotted box anyways. And then there are diagonals of this box that create asymptotes that give a more description of what the parabolas look like, how wide or how skinny they are, basically. Now, we're not going to get into that here too much, but notice that we have A and C, but B is not really mentioned here. But what we do have is this equation that actually relates them. And this is true for both of these scenarios, vertical or horizontal. And I guess I'll call this the foci equation. And the foci equation is basically Pythagorean theorem. A squared plus b squared is equal to c squared. Now, something to remember is that hyperbolas have a minus in the middle, where ellipses have a plus in the middle. The foci equation for hyperbolas has a plus, opposite sign as what you see there. But with ellipses, it's the opposite. Ellipses have a plus in the middle, but their foci equation has a minus in the middle. A is still the distance from the center to a focus, and A is still the distance from the center to a vertex, and C is still the distance from the center to a focus. B is a little more obvious there for ellipses, but we'll talk about that, I think, in the next problem. And I think with that being said, we have all the information we need to continue. So maybe that's okay. So we have H and K, now all we need is A and B. Well, we actually have A and technically C. A is actually this guy, it's 5. It's the distance from the center to a vertex. What about the distance from the center to a focus? Well, if you notice here, all we've really done to find this distance is really subtract the y values of the center y value and the vertex y value. And if you think about it, 4 minus negative 1 is 5, and negative 1 minus negative 6 is negative 1 plus 6, which is also 5. So basically you do top y value minus bottom y value to get the distance between them. Okay. The same is true horizontally. Do the later one minus the prior one, basically. Or you can just take the absolute value of the difference. That works too. So notice here the y value of this focus is this guy. And if we do that minus the y value of the center, negative 1, we'll actually just get the following. So we'll get little c. So there's a difference between capital C and lowercase c. Lowercase c is the distance, capital C is the point, which is the center. So I often curl the top to distinguish those. So c is going to be the difference between negative 1 plus 3 radical 3 and this y value, which is negative 1. So notice the double negative here makes us positive, and that cancels with this. So lowercase c is actually just 3 radical 3. And how I was able to spot that at the beginning is to notice that really what we're doing is taking away an amount and adding an amount here from this common point, negative 2, negative 1. So actually, if you were to go from this y value of the center up 3 radical 3, you get to this focus above. And if you were to travel 3 radical 3 below from the center, you get to this focus below. So that's kind of interesting. So we have A, we have C, we have H, we have K. But now what about b? Well, we use our focus equation, a squared plus b squared. Let me write it out. So it's 5 squared plus b squared. We don't know what b squared is equal to 3 squared. Well, 3 radical 3 squared. Okay. 5 squared is 25. 3 squared is 9. Radical 3 squared is just 3 because the radical and square cancel. That's 27. So notice subtracting this 25 to the other side gives us that b squared is equal to 27 minus 25. That's 2. So this would tell us that b is the square root of 2, but in actuality, we don't even need to find b. B squared suffices because we can just plug it in to our equations and we'll be good. Now remember, since we have a vertical set of parabolas here, it's a vertical hyperbola, so we'll actually be using this one down below, this equation here. Basically, y is going to be in front. Y minus k, x minus h, a squared on the bottom of y, so a is always in front for hyperbolas, and then b squared on the bottom for x. So altogether, we have y minus negative 1, which is y plus 1, double negative, right? Over a squared, that's 5 squared, that's 25, minus, because it's a hyperbola, x minus h, x minus negative 1 is x plus 1, x minus negative 2 is x plus 2, there we go, squared, over b squared, which is 2, equals 1, and that is our answer. Whew, nice. Now, something I should probably also mention that is very, very, very helpful, especially if you want to try to do these types of problems without the visualization, is this following fact. If your center is h comma k, then your vertices are going to be h comma k plus or minus a, and your foci will be h comma k plus or minus c. Now, this is actually only for vertical cases. For horizontal cases, you would add, we do a plus or minus basically to h instead of to k. So here we're changing the y value by adding and subtracting an amount. And that makes sense because you're going up and down an amount for v. For v, you go up and down by a, so hence the plus or minus a. For the foci, you go up and down by c, so hence the plus or minus of c. Now again, that's only affecting the y values because this is a vertical case. For a horizontal case, k would stay the same, but then you have a plus or minus a and plus or minus h, plus or minus c on h. Okay? And this actually works exactly for ellipses, as we'll see soon enough. Okay, with that being said, let's move on to number 4. Okay, so for 4, well, we actually learned a lot from what we just discussed with hyperbolas. In fact, the same basically is true for ellipses. Essentially everything is true except for the shape. So I'm going to lecture a little bit on that just to remind us what's going on for ellipses, and I guess I can do it over here, maybe it's better. So for ellipses, we have horizontal and vertical cases, of course. So the equations, I'll just start off with the equation. We have x minus h squared, y minus k squared. We have a squared and a squared and b squared as denominators. We have a plus in the middle. In the vertical scenario, almost looks identical, only the a squared term is actually under y instead of under x. That's really the only difference. Now, why is that the case? It doesn't seem like a is different from b at all. Well, for ellipses, unlike with hyperbolas, a must be larger than b. That wasn't necessarily the case for hyperbolas, but for ellipses, it is actually the case. Another thing, of course, is that the center is h comma k again. And we have our foci equation, a squared minus b squared is c squared. And notice this makes sense. Even though we have a subtraction equal to a square, that's actually okay because since a is bigger than b, this will always be a positive number as a result. Okay. Now, horizontal ellipse will look like an elongated circle, well, horizontally elongated, and for vertical, it looks like this. Your center is smack dab in the middle. You have a minor axis, which is a shorter axis of symmetry, major axis, which is the longer axis of symmetry. Okay, your vertices are the points on the major axis. So these are the vertices. The foci are somewhere in between the vertices and the ellipse, or in the center of the ellipse. So it's kind of backwards of what we saw for hyperbolas. Because hyperbolas, again, it's kind of based on parabolas, but here the parabolas, I guess, are kind of inside. I guess you can kind of think of it like that. In fact, it's kind of interesting, but the closer the foci are to each other, the more circular shape this will look. In fact, when the foci are equal, they equal the center, and then you just have a circle. So it's kind of interesting. This is basically a generalization of a circle. Now again, the distance from a vertex to the center is A, and the distance from a focus to the center is C. B here is this distance, the minor axis endpoint distance from the center. Okay. Great, so I think with that being said, we're good to go, and maybe let's just kind of start. There's something more I want to say that we kind of finished off saying with number 3 before, but we want to get this into the standard form first. Notice we have to complete the square, which we saw with number 1, so that's good. So let's look here at the x's and y's, group those. Notice now, though, we have a number in front of the square term for each of these. Maybe I should box this off to the side. It doesn't get in our way. So let's see. I want to basically factor out the number in front of the square for each of these. So 9 I'm going to factor out. Notice we get plus 2x. Okay, leave a little bit of a space. Here I'll pull out the 4 in front of the y squared term, and that'll be consequently negative 2y. Okay, so these kind of look very similar, and then I'll leave some space, and I'll actually add that 23 to this side, and I think we have enough space, hopefully. Now remember, I want to add some term here and some term here. There's a little bit of a difference from number 1, though, because since we pulled out something, we'll have to distribute that back in to see what we're really adding to the left side. Okay, we're not just going to add this number to the other side. We have to distribute first to see really what it is. Now that we have no number in front of the square term, though, we can simply half the middle one. Half of positive 2 is positive 1. Half of negative 2 is negative 1. So there we go. We've completed the square for these, and we have those coefficients in front now. Great. What about on the other side? Well, let's see. We're adding 1 here because that's 1 squared. Negative 1 squared is also 1. So if you expand those out, you get each of those trinomials in parentheses. So that's fine. But now again, when you distribute that 9 to those two terms, you get those. That's fine. But for this one, you get a new term that wasn't there before that we're introducing to each side to balance the equation. So after distributing this, we really see we're actually not adding 1 to this side, we're actually adding 9 to this side. So I have to add 9 to this side. Similarly, here, what am I adding? Adding 4, right? Because 4 distributes to 1 and you get 4. Perfect. So in reality, this is 23 plus 9 plus 4 is 13. So that's 36, which is a nice square number, so that makes me happy. Still not quite in the form we want, though. Standard form is so that 1 is on one side. So that 36, we needed to make it a 1 somehow, so naturally we'll just divide everything by 36. Divide, divide, divide by 36. Now what's really nice here is that obviously that side becomes a 1, so that's fine. What's really nice here on the left side is that 9 goes into 36 4 times, 4 goes into 36 9 times. So we have x plus 1 quantity squared over 4 plus y minus 1 quantity squared over 9. Perfect. So this is actually in the form. Notice, the larger denominator is under y. A was our larger denominator, under y means it's vertical. So it's going to be a vertical scenario. We know the center is what is subtracted from x and y. Right, so we need to change the signs, basically. Remember how we did that. So change the sign of that positive 1 to get negative 1, change the sign of that negative 1 to get positive 1. You could also do what I did at the beginning and write this as x minus negative 1. Remember that? Okay. So h is negative 1, k is positive 1. Perfect. But now here's how this goes as far as graphing. You look at a and b. Now a is not 9, b is not 4. They're the square roots of those numbers. So maybe I'll write here, a is the square root of the larger one, square root of 9 is 3. B is the square root of the smaller one, and the square root of 4 is 2. Okay. What about c? Well, remember, c squared is a squared minus b squared. So from this, we can tell that c squared is equal to 9 minus 4. It's a squared minus b squared. Okay. That's 5. So c squared is 5. So that means c is the square root of 5. Okay, so we have a, we have b, we have c. Now, in fact, we really only need a and b to get a good graph. So I'll show you what that looks like. Maybe I can do it here, I guess. Should be okay. Now negative 1 comma 1 is over here about. I'll make this maybe a 5 by 5. Should be enough. Trying to make it accurate again, like usual. Okay. So now the square root of the number under y is our vertical change, right? So we're going to go up and down by a, so that's 3. So if you go up 3, you get this vertex, and if you go down 3, 1, 2, 3, you get this vertex. So it's V1, let's say, and V2, and this is our center C. Now if you go left and right by the square root of the number under x, then you'll get the horizontal change. So that's 1, 2, 1, 2. These are the minor axis endpoints. Connecting these gives us a lovely ellipse. Hopefully to scale, doesn't look too bad. Now again, does this really matter to us? Kind of. I mean, we can interpret what the vertices are from this. So it looks like V1 will have the same y value, the same x value as the center, negative 1. But now if you go up 3 from 1, you go 1, 2, 3, 4. So it seems like V1 is going to be the point negative 1, comma 4. And V2, I guess, would be the point negative 1, comma, let's see, go down 3 from 1, you get 1, 0, negative 1, negative 2. That's negative 1, comma, negative 2. Okay, great. Now we also want to find the foci. Now, what's the foci? The foci are these points that are in the middle somewhere. So we have to travel from the center up and down by radical 5. This is kind of abstract, but basically all we're doing, notice, is if you look at the center, if you add a to the y value of the center, because this is a vertical ellipse, you get V1. If you subtract a, which is 3 from this, 1 minus 3 is negative 2, so you get that vertex. So I'm going to do the same with C, and I'm just going to leave it like this. I'm going to say the foci are negative 1, comma 1 plus or minus radical 5. Plus radical 5 for the focus on top, and negative radical 5 or minus radical 5 for the vertex down below, or for the focus down below. Sorry. So I'm not writing it as F1 and F2, I'm just writing it as F with that plus or minus notation, and I'm okay if you do that, provided it can't really be combined. And I'll kind of explain what I mean right now by showing you a different way of doing this without the visualization, with the knowledge we saw from number 3 at the very end. So remember that if the center is h comma k, which it is here, then the vertex, because this is vertical, the x value will stay the same, but the y value is changing because it's vertical. The y value was 1 for the center, but now we're doing plus or minus a, because a is the distance from the center to the vertex. So notice, if you actually do this out, 1 plus 3 is 4, 1 minus 3 is 2, negative 2. So we get those. If you wrote this, I mean, it's okay, but I'd rather see this. If you can combine them and write them individually. But for the focus, notice if we just look at the center, negative 1, comma 1, and again, it's vertical, so change the vertical component, y, by adding or subtracting c. And you get this. This I'm okay with leaving because, well, you can't combine those. Otherwise, you would write negative 1, comma 1 plus radical 5, negative 1 minus 1, negative 1, comma 1 minus radical 5. There we go. But I think this is fine. Okay, so I hope this last bit helped. Once you find A and C, you're good to go once you have the center, basically, without any visualization. So with that being said, let's move on to number 5, and let's see if we can use now our knowledge of all of circle, parabolas, ellipses, and hyperbolas to do the rest. Okay, so here for number 5, we're asked to find the equation of a circle, but this one's actually kind of strange. I think this is actually a very difficult problem. I don't expect anything this complicated to be in the exam, but I think definitely this is a very good exercise. So let's see if we can tackle this together. So we want to find the equation of a circle with a diameter whose endpoints are these points. So we kind of have to recall what diameter means. So if we have a circle with a center and a radius, if you travel that radius in opposite directions of a center, you get the diameter, which is usually called d. So d is equal to double the radius, basically. It's the entire width of the circle from one endpoint to the extreme opposite side. So it's the longest center you can have, or longest distance you can have within a circle, basically. And it also passes through the center. So it's double the radius, basically. Okay, so what you notice is that we have these 2 points, so we can plot these if we want, that's fine. But really what we need to do is find the distance between these points. Do we know how to find the distance between 2 points? we can use distance formula. Also, notice the center of the circle here is smack dab in the middle between these two endpoints. So if I call these 2 points like capital A and capital B or something like that, the center is the midpoint of A and B. So we can recall distance and midpoint formula, and then we'll basically be done. We'll have the distance, which is D, half that to get the radius, because divide by 2 you get R. And the midpoint of these 2 points is right away the center. Once you have the center and radius, we can use a standard form that we know for circles, and then find our equation. So that's the goal. Now I'll try to maybe plot these points a little bit to get an idea. And there's some visualization that may help kind of guide us through things. So 0, negative 1 plus radical 72. Radical 72, well, that's a little bigger than radical 64 and a little smaller than radical 81. Maybe not a little, but you know what I mean. It's basically going to be like 8 point something because it's in between, the inside's in between 8 squared and 9 squared. It's one way to think of that. So if you wanted to go up 8 point something, you get to negative 1 plus radical 72. But this is adding radical 72. If you go down by that same amount, and try to make this somewhat accurate, radical 72, then we get negative 1 minus radical 72, like that. Okay, now 0, negative 1 plus radical 72 is up here, and 6, so this, we agree this is like 8 point something, so again, to be somewhat to scale, we're going to call that 8 point something, a little less would be maybe 6, let's say. So 6, the lower one is down here. Perfect. So it looks like the center passes through these 2 points. So I'm going to erase this radical 72 depiction. And now we have this distance here, this straight line that we need to find the distance of. Okay, that looks more or less okay. Now, what you'll notice is halfway in between them will be the center, and then the distance of this is the diameter, actually. Also, what you may notice is we've actually created this right triangle, which we can use Pythagorean theorem with. We actually said earlier this is radical 72 plus radical 72. So that's actually 2 radical 72. So if we just take advantage of a squared plus b squared is c squared, then we have that our distance squared is actually going to be the square of this plus the square of this. Now, it's not obvious, but if you use distance formula, this is actually the same thing. Just think about it. Distance formula, just to remind us, let me write it below, is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Basically, it's the difference of the y squared plus the difference of the x squared all under a radical. The radical part, I think, is justified because if you square both sides, you get d squared is equal to the sum of squares of 2 numbers. If you subtract the x's, let's say x2 minus x1, that's 6 minus 0, that's 6 squared, so that's going to be this guy. Notice it's just the x change, basically. The y change will be y2 minus y1. Notice we do this minus this. I'm sorry, I kind of made a mistake. This should have been negative, my mistake. Probably all looking at me funny now, but yeah. This was a negative here. For some reason, I wrote it wrong at the beginning, but I graphed it correctly. But if we do y2 minus y1, let's say this minus this, if you distribute the negative here, you get positive negative. So the negatives will combine to negative 2 radical 7. That'll be positive 1, so that'll cancel with this negative 1. So you get negative 2 radical 7, but when you square it, it's positive anyway. So the squaring basically ignores any difference of the plus or minus in between, basically. So if we subtract any order, squaring will get rid of the negative you would have gotten if you subtracted in a different order. Something to think about. Okay, so I'm just emphasizing that this idea is the same as the distance formula. So even though I mentioned distance formula earlier and not necessarily using it, I kind of am. Just kind of more visual. Okay. Another trick I'm going to use is that when you square this, 2 squared is, of course, 4. Radical 72 squared cancels a radical, and you just get 72. 6 squared, of course, is 36. I'm going to notice something a little clever. Not super clever or anything, but just a little bit. There is a relationship between these two. 72 is double 36. So 4 times 2 times 36 is actually 8 times 36. 36 is, of course, 1 times 36. So if you factor that out, you get 8 plus 1, which is 9 times 36. Why am I doing that? It just makes it a little easier to square root, because when you square root now, you get that d is equal to the square root of 3, the square root of 9, times the square root of 36, which is 18. So the diameter is 18. That means the radius is half of the diameter, which is 9. Fantastic. Okay, so that is explained. This total distance seems to be 9. What else? The midpoint. How can we find the midpoint visually? Well, the equation of the midpoint is just that it is the average of the x values comma the average of the y values. So x1 plus x2 over 2 plus, or comma, y1 plus y2 all over 2, like this. Okay, now this makes sense because if you look halfway between the x values, that's 3, which is about here, let's say, and halfway between the y values, we already agreed was -1. That's why I drew that earlier. So you get this point, which is 3 comma -1. So it's just meeting halfway between the x's and the y's, joining those, and you get the midpoint. So this is the center. Now, I didn't quite do it with the formula. Again, I did it visually. But again, if you add these x and y values and divide by 2, you get 6 over 2 is 3. If you add these, the radicals cancel. -1 minus 1 is -2. Divided by 2 is -1. So that works out nice. So we have the center is the point, 3 comma -1. This is h, this is k, that's r. Right away we're done. We have x minus 3 quantity squared plus y minus -1, which is y plus 1 quantity squared, equals 9 squared, that's 81. Done deal. Move on to 6. All right, so for 6, we want to find the vertex, focus, and directrix of the parabola whose equation in general form is y squared plus 20x plus 2y plus 41 equals 0. So remember that standard form for a parabola has either an x squared or a y squared, and then the other one that's not squared is multiplied by 4p. Clearly here the one that's squared is y because we have the y squared. So I want to complete the square. Notice if we had y squared plus 2y, this would complete as y plus half of this squared, which is y plus 1. Okay. So now, how do we find what we need to add to that? Well, notice if you expand this out, you get plus 1. So we need a plus 1 here. There's a few ways to do that. What I'm going to do actually is I'm going to subtract these two non-y terms to the opposite side. So I get -20x minus 41. But actually, if we had split this up as 40 plus 1, there's a few ways of seeing this, but I think this is a nice way of doing it. You split it up as 40 plus 1 and borrow that 1 to be here. Then subtract that 40 to that side, you get this. If you don't like that, you can just do it the usual way, subtract 41. So you have -41 and then add 1 to both sides, and look at that, -41 plus 1 is -40 still. So regardless, we end up getting something like this. And again, if you're not sure, you can always expand things out, move everything around to get back to the original, and if you get exactly the original, you've done things correctly. Okay, so one side squared, the other side has 4p in front. There's nothing in front here yet, but whatever's in front of x, I want to pull that completely out. Even if this can't be divided by that, but in this case it can. If you pull out the -20, dividing that by -20 just gives you x. -40 divided by -20 is +2, so there we go. So right away I can tell what the vertex is. Okay? The vertex is h comma k. It's always x minus h, y minus k. It's always like that. This is x minus -2. Remember, change the sign of the number next to x. Change the sign of the number next to y. So -2, -1. That is the vertex. What about this? What is this? Remember, this was 4p. So we can actually say that 4p is equal to -20. Dividing by 4 gives us that p is equal to -5. Since y is squared, this is a horizontal case. So let's do some graphing to get a visualization here. -2 comma -1 is, let's say, down here. Okay. If this is -5 and we know y is squared, so it's horizontal, that means it's going to face in the left direction, in the negative horizontal direction. And in fact, p is -5, so we're going to travel 5 to the left. 1, 2, 3, 4, 5. So this lands us at -1, 2, 3, 4, 5, 6, 7 by counting. Straight line distance, so we get something like this. That's our point F, or focus, which is -7, -1. So the focus is -7, -1 by counting. The directrix is going this distance, 5, but in the opposite direction. So we count 1, 2, 3, 4, 5. So you get over here, this point, which is on this vertical line, x equals 3. And that right there, that is the equation of the directrix. So the directrix has equation x equals -3. So there we go. We got the vertex, focus, and directrix of this parabola. We're good to go. But before I move on, I want to describe something that's kind of interesting. And that's that if your vertex is h comma k, then the focus will be h comma, well, in this case, we're going to change the x values because it's horizontal. So this will be h plus p comma k, and the directrix will always be x equals h minus p. Now this is for vertical scenarios. This is basically a formula to do things non-visually. And it makes sense because you're adding p. Now if p is negative, you're really subtracting p. But if p is positive, then you're moving in that direction. So this is actually independent of p being positive or negative. This just works. Okay? But for vertical. This is for horizontal. What am I doing? This is for horizontal scenarios, like the one we have here. Vertical is you change the k's instead. So let me actually write it out. So for vertical parabolas, the vertex is hk. Given that, then the focus is going to be h comma k plus p, and then the directrix will be x equals h minus p. Kind of seems weird, but remember, p could be negative. So if p is negative, your directrix is actually going to be above, not below. Which makes sense because you'd be facing down, your directrix is above the vertex. Because you'll have h minus a negative, which is double negative is positive. So something to think about that I think is really useful if you wanted to do things non-visually. But honestly, visualization is more intuitive. It's quicker. But very often I like showing these because it's nice to think about it, just to give you an alternative approach. Okay, so with that being said, let's move on to number 7. All right, so for number 7 here, we're asked to find the equation of the ellipse with vertices given and with a minor axis of length 4. So we're given the length of the minor axis, which is interesting because if you think about it, I don't know if this is horizontal or vertical, but let's just imagine it's horizontal for a second so we can talk about the minor axis. If the minor axis has length 4, that means half of that length is going to be b, because that's just the distance from the center to each minor axis endpoint. So right away, we can actually tell that b is half of this length, so that's 2, just from this part here. The minor axis is length 4, that tells me right away b is 2. Remember that for the standard form of an ellipse, we need h and k, of course, the center, which we can actually find by symmetry of the vertices. So if we plot the vertices, look halfway in between them, that's the center. So h and k are good, b is good, and a will actually be half the distance of, well, the distance from center to center, or vertice to vertice, or vertex to vertex. So here, the distance from vertex to vertex is the length of the major axis, half of that is a. So we can actually maybe use this image because notice since 5 is the same for the y values aren't changing, the x values are changing. So that means this should be y equals 5. And we have, let me see, it's y equals 5, x equals 3, and negative 5. So this should be x equals negative 5. I'm going to try to do it justice, but I don't know if it'll be exact. But let's just say this is 3, this is negative 5, 1, 2, 3, 4, 5. I'm kind of doing it okay. And then this is going to be at y equals 5. So it's going to be 1, 2, 3, 4, and 5. So if we were to plot these points, this is 3, 5 for one of the vertices, and this is a negative 5, 5 for the other vertex. Of course, not to scale, but you kind of get the idea. Now also, this is totally not to scale here because we already agree that these are 2 each. But still, we can count the distance here. It's quite literally just the difference between these numbers. 3 minus negative 5 is 3 plus 5, which is 8. If you half that distance, you get 4. So that means a is 4. And if you travel 4 from here to here, just count backwards. 1, 2, 3, 4. You land at So this is, again, a little off, but you end up getting here, basically. So, again, the scaling's off, but you kind of get the idea based on that image. Okay? So this x value is -1, so it's -1, 5. There we go. -1, 5. Let me write it like that, I guess. So we have our center is -1, 5. That's h, that's k. And we know it's horizontal, and we're able to tell because, again, the x values are changing, not the y values. So we're done. We know it's going to be x minus h. X minus -1 is x plus 1 squared over something. We'll get to that in a moment. Plus y minus k, it's y minus 5 squared over something, equals 1. Now, what goes in the denominator of what? Well, remember, for ellipses, the larger denominator dictates if it's horizontal or vertical. The larger under x means it's horizontal. This is clearly horizontal. The larger one is always going to be a squared, which is 16. B squared is 4. There is our equation. Now, I did this visually. I want to show you maybe a non-visualization, non-visual way of doing this. So if you look at this, we can tell right away that the one that is not changing, that is that value of the center. So I know right away the center is going to be something, 5, just looking at that. I also know that the vertex is h plus or minus a, 5 now. Now, h plus a is going to be the larger of those two x values, which is 3. H minus a is going to be the smaller of those two x values, which is -5. This is just a system of equations, a very easy one, in fact. Adding straight down, the a's cancel, 2h is equal to, well, I guess, a -2. Dividing by 2, we get h is equal to -1. And that is definitely true. We found h to be -1, so there you go. Again, I'm kind of dealing with a non-visual way of doing it. We already finished the problem, but visually. Okay? So non-visually, without this visualization, you can still figure out h and technically a as well. Plugging this back in, -1 plus 4 is 3, so a is 4, so we have that. And then what about b? Well, b was just half of the length of the minor axis, so that we did non-visually as well. So it's nice. We found h, k, a, and b non-visually. We know that k is the one that is not changing, so the y is not changing, the x's are changing, so it's horizontal, so the larger one goes under x. We could do it non-visually. Fantastic. So with that said, let's move on to number 8. Finally, and then the review will be done. Okay, so finally we're at number 8, the last problem for the review. And this is probably the longest one, I think, because we need to find a few things here to hyperbola. Based on this equation, we need to find the center, vertices, foci, and asymptote equations. Now, we kind of did that for the ellipse a while ago, but for the hyperbola, it's the same kind of idea, only, well, we know hyperbolas have kind of a different focus equation and so on, and different kind of format and graph. But asymptote equations, we haven't really discussed those too much. We discussed, asymptotes are the, I call them the diagonals of the dotted box. I don't really describe that too much. We may, I think, talk about that a little here visually, but it's actually not that bad. So what are we going to do? Well, first I want to get this in standard form for hyperbolas. We need to complete the square. Notice, though, we only have x that needs to be completed. Why is that? Well, it's because y is already a completed square. Since there's no y term, no non-square y term, we don't need to worry about that. So that's nice. And in fact, if you think about it, that kind of means that the y value of the center is 0 right away, because y squared is the same as y minus 0 squared. We'll see that in a moment. So we know how this works. We're going to grab 4x squared and -8x, and I want to pull that number in front of the x squared term out. So pull the 4 out, we get x squared minus 2x. We need to add something to this. I'm going to keep that negative y squared on this side. I'm going to add that 60 on that side. It doesn't really do us any good on this side. And realize that when you half this, you get 1, -1. So in fact, if you expand this out, you get x squared minus 2x plus 1. Distributing the 4, we're really adding 4 to the left, so we should add 4 to the right as well. Minus y squared is equal to 60 plus 4 is 64. Again, we have a nice square number like we saw for the ellipse problem a while ago. So that's good. And now what? Well, now to make this 1, because remember for the standard form we want 1 to be on that side, we're going to divide every term here, all 3 of these terms, by 64. So that's 1. That's fine. This is y squared over 64. Okay, and here we have, well, 4 goes into 64 16 times. Okay, so we have x minus 1 quantity squared all over 16. Now, specifically, to be very, very specific here, this is x minus 1 squared over 4 squared minus y minus 0 quantity squared over 64 is 8 squared equals 1. So we know a is the one in front, not the larger one for hyperbolas, it's the one in front. So I know a is 4. So this tells me a is 4. Perfect. It tells me b is the other one, so that's 8. Square 2. We get that from both of these from that. Also tells me that the center is 1, 0. Change the signs of these, you get positive 1 and 0. So the center is 1, 0. So that's actually an answer, so I'm going to box that because we want to find the center. So there we go, we got that one. Nice. To find the vertices, well, let's see, is this horizontal or vertical? Well, I know this is horizontal because x is in front, that's the hyperbola scenario. For ellipses, it's the larger denominator which dictates the orientation, but for hyperbolas, it's the one in front of the subtraction, right? Okay, so I want to change the x's by a, the x value of the center by a. So for the vertices, we're going to get 1 plus or minus 4, 0. And we'll get 2 vertices. So v1 I'll call the positive one, 1 plus 4 is 5, 0. And v2 I'll call the negative one, 1 minus 4 is negative 3, 0. And again, you can do this part visually if you want. I'll actually give the visualization in the moment when we get to the asymptote part of this problem. That I think will require the visualization because again, we haven't really seen that at all up to this point. And finally, for the foci, before we get to the asymptotes, I'll describe that over here. We need to discuss the foci equation for hyperbolas, which is basically a Pythagorean theorem. And the nice way to remember that is it's opposite sign of the sign for the equation. So we're going to have a squared plus b squared is equal to c squared. So c squared is equal to a squared, which is 16, plus b squared is 64, so that's 80. So that means c is the square root of 80. And actually, you can break that up a bit, right? As 80 is 8 times 10. You can't square root those, though, but 10 is 2 times 5. So in fact, 80 is actually 8 times 2 times 5. That's 16, notice. So you can't square root 5, but you can definitely square root 16. That's 4. So this actually broken up is 4 radical 5, or I guess simplified is the word. So that radical simplified is 4 radical 5. So if you add and subtract that to the x value of the center, you'll get the foci. So I'll write that in plus or minus form. For the foci, we have 1 plus or minus 4 radical 5, 0. So I hope you see how I've done this here non-visually based on what we've kind of established in kind of the previous problems. Now that's good. Now I'm still going to show the visualization over here. Hopefully we can figure out the asymptote situation. Let's take a look. So we have 1, 0. I'm just trying to figure out the size more or less what we need, but it seems like we're kind of gravitating in the first quadrant just based on these numbers. So 1, 0 is going to be over here. I'm going to make this maybe a 6 by 6, I think should be okay. 1, 2, 3, 4, 5, 6. Let's go up to 8. Doesn't really matter, I guess. Okay, so it's a little crooked, but I guess it's not too bad. So basically what we're going to do is we're essentially going to create a, well, we want to create a hyperbola. But the way I'm going to do it, I'm going to make that dotted box first. Now that dotted box is very, very much like how you make an ellipse. Only instead of an ellipse shape, it's a dotted box shape. And then I'll kind of go from there. So the center is 1, 0, that's here. I'm going to go up and down by the square root of the number under y. Y is vertical. So I'm going to go up and down 8. So 1, 2, 3, 4, 5, 6, 7, 8, that's right here. Okay, so notice this is, well, okay, so that is, that's not part of what we found, so I'll explain that in a moment. So that's going up 8. You need to go down 8 as well. So we go down 8, it's 1, 2, 3, 4, 5, 6, 7, one more 8. So we get 1, -8. And again, that's not part of our what we found yet, but you'll kind of see it come together in a bit. And now I'm going to go left and right by the square root of the number under x, which is 4. So to go to the right, 1, 2, 3, 4, we get to this x value 5. 5, 0, that's one of the vertices. If we go 4 the other direction, we go 1, 2, 3, 4, that's -3, 0. That indeed is the other vertex. So that's good. So we see that. And now, what I'm going to do now is we could make an ellipse, but this is not an ellipse equation, or not an ellipse problem anyways. So we're actually going to create this dotted box. Basically a dotted rectangle. Using these points as kind of like the endpoints of the, or I guess midpoints of the sides. Doesn't look super pretty because of the scaling and all that, but you kind of see the dotted box there. Okay, now the vertices are the ones that lie on, well, it depends. So for the ellipse, it's the larger one, but remember that for hyperbola, it's the one in front. The one in front is x, so it lies on the x ones, the horizontal ones. Okay, so we're going to have these opposite facing parabolas. To be specific, though, what we're going to do is we're going to create these diagonals. So these diagonals go from corner to corner and crosses through the center. Our main goal right now is to find the asymptote equations, but I want to show a little bit of graphing. We're almost done, so it's not too bad. So if we stem from these vertices here and here, I'll start with the right side first. I want to basically hug these diagonals. It's kind of eventual, but I do it sooner than later, just to kind of give a nice visualization of what the graph will look like accurately. Now the black part is the graph, not the red or the dotted box. That just kind of describes how you build that basically. What about the foci? Well, the foci are actually going to be somewhere over here and over here. Now 80, this is 1 plus radical 80, 1 minus radical 80. So radical 80 is a little less than radical 81, which is a little less than 9. So 1 plus a little less than 9 is a little less than 10. So it's actually going to be a little far off. But it's somewhere over there. It doesn't really matter. The whole point is that's the focus of that parabola. This is the focus of that parabola. So if you want to label it F1, F2, however, that's fine. I'm just calling them F, just for reference. So that's how the graph looks. Great. But now what about the asymptote equations? Well, these are just lines. And lines have slope and I guess y-intercept, which we can kind of find here. I did it somewhat justice, but we'll actually see exactly what they are in a bit. Really what I want to use is the center as a point that is on each of these lines, and I want to use point slope. So I'm going to notice that if you go from this point to the diagonal here, you go up and over. So here the slope is going to be positive 8 over 4. 1, 2, 3, 4. It's basically b over a. So this is b over a, that's 8 over 4, which is 2. Okay. For this one, we go down and over, so it's negative that. So here the slope is negative 2. Okay? And by point slope, just to remind us what point slope looks like, that's y minus the y value of a point equals the slope m times x minus the x value of a point. Now the point I'm going to be using is the center, 1, 0. Okay? So basically what we'll be getting for the asymptote equations, I don't really have too much space, maybe here, let's see. So we're going to have y minus the y value of this point, which is 0, equals the slope, which is plus or minus 2, times x minus the x value of the point, which again is the x value of the center, which is 1. So there we go. This is the equation of our asymptotes. There's two equations in one, though. So we have y is equal to, let's do the positive one here. If you distribute that, you get 2x minus 2. And for the negative one, you get negative 2 distributed is negative 2x plus 2 because negative times negative is positive. So there we go. These are the equations of our asymptotes, and you can kind of see that this one will have a y value, a y-intercept of negative 2, and this one should have a y-intercept of 2. So somewhat to scale, but not quite close, though, so we can see that. The negative slope 1, negative 2 over 1 down like that, but the y-intercept is at 2, and the positive slope 1 has a y-intercept of negative 2. Perfect. So there we go. I've given the asymptote equations, the center, the vertices, the foci. It was the longest problem so far. Well, I say so far, but that's the end of the review. That's it. So I hope we all enjoyed this. I hope we understood and liked the explanations I've given. Again, I've tried to be pretty elaborate and give some type of alternative approaches to some of these problems. There's definitely a good set of problems here. The ones you'll see on the exams, I don't think will be as complicated as a few of these were, but these I definitely think give good practice and give you a good study material for the exam. So I wish you all luck in the exam, and with that said, that concludes this video.